Hi. So in the last video, we saw how these parameters were very important, and these parameters were our hyperparameters, as I said. So we need to tune them. So we will be using a technique known as hyperparameter tuning, and we will be using a randomized search CV, which will give us the best hyperparameters for our random forest model. Why we are particularly selecting random forest model? Because random forest model gave us a very good accuracy over here. That was R2 score over here, that was 88%. So we'll be going forward with that only. So you can also hyperparameterize the other linear algorithms as well, linear models as well, but time being I'm using I'm using random forest algorithm. So let's see what we get. So over here I need to get the transformer list, that is nothing but the categorical list, and then I will apply the get dummies function from pandas, and I get this train, and then over here what I will do is I will apply train test split. Okay, once I apply train test split, so basically I'm going in other direction for only the random forest classifier, where instead of using column transformer for kind of getting this thing, getting the categorical variables, instead of using column transformer, I'm using get dummies. Get dummies is also one hot encoding only, and the same kind of result we will be finding if we use column transformer also. There's no difference. Then I will use train test split, and then yes, this is a very important one. Regression object is equals to decision tree regressor random state 0. I'm fitting it, and then I'm plotting the decision tree. Now you just understand, in the previous past video I said that when we are building decision tree, it will try to go till the end. Now you will see that how it is trying to go till the end. Okay, so this will take a little bit time, and you see how much tedious calculation this is doing at each node, right? This will do a lot of calculation because this is not perfectly hyperparameterized. The max depth is not set, the criterion is not set, anything is not set over here. It is by default taking some random value and it is doing it. And you see how bad and how big the decision tree would look, and we see that the execution time is also taking too much. Okay, so this kind of model, when it goes to production, this kind of model becomes little bit heavy, and this kind of situation takes a lot of computational power as well. So yeah, we have to be very careful here, and we will see something over here like let the decision tree get plotted. I think it is taking more time than required. Yup, we get the decision tree here. So if we see the decision tree here, oh my god, this is so much. So I have to scroll a lot down here. So if we see this very big, you can see this last end, it tries to classify this till this last end, and to be honest, this much big decision tree is not required only. Okay, we can cut or we can prune this decision tree. Prune in the sense cutting, not require everything, but require only the important part from which we can manage the things. That is what we are looking in decision trees. So you see that this is totally in case of overfitting only. But when this kind of decision tree object is made into production, it will give you blunder results. So we have to optimize this. So for optimizing that only, we are using this hyperparameter tuning technique. So how we will go ahead with this? Okay, so this is how the basic tree looks. So there is some parameter known as cost complexity pruning path. This cost complexity pruning path is responsible for pruning the leaves or pruning the branches of this decision tree. Now on what factors does the pruning happen? The pruning happens on the factors like there are various factors which affect pruning. There's no such exact factor which takes place, but I will just give you a glimpse of what actually this is. It says that cut off or chop off the branches, when you are having something like 50-50 kind of situation, or like 75-25 kind of situation, you keep that, you allow a little bit of misclassification, because in future you will be getting data, you will be getting a new kind of data. And if your model is already overfitted, the model will always try to predict whatever the model has been trained on. Let's say the model has been given 100% accuracy for a label yes and 0% accuracy for label no. If you give a new data set, if you give some new data point, it will by default classify it as yes. It will not even check whether it can come under no or not, even though it was no. Human brain can say it as no, but your algorithm is saying it as yes. That means that it has totally overfitted. And when it comes to totally overfitting, this is the scene which happens, this big decision trees. So we have to chop them off. So in order to maintain consistency, or in order to maintain some kind of computational stability with precise accuracy, we use complexity path. So this is nothing but cost complexity pruning path, and when we execute this, we get the CCP alpha values, and CCP alpha is our main hyperparameter, along with max depth, n estimators, min samples leaf, min samples call leaf. So by these 5 or 6 parameters, random forest algorithm must be hyper tuned. So when you try to look at CCP alphas, what you will get CCP alpha is, you will be getting something like this. If you try and see, you will be getting a numpy array of values. So we will be using this over here. So for alpha in CCP alphas, regression is equals to decision tree regressor of alpha, regressor.fit xtrain ytrain, and alpha list dot append regressor. So we are appending this regressor models into this. When we do shift enter, this will take a little bit time because it has to process this all CCP alpha values, right? Yeah, it has to process those all CCP alpha values. And once if we see the alpha CCP alpha list, once if we see the alpha list, you will understand. See, decision tree regressor alpha CCP alpha is equals to 1.67 random state 0, 1.670 random state 0, 1.25 random state 0. So this alpha list is having objects of decision tree regressor. Now we are already having decision tree regressor, no? So we will apply a for loop and we will calculate the training score and testing score. So reg.score xtrain ytrain, reg.score xtest ytest. Or maybe this should be something like yeah, basically the regressor object has only this thing only, reg.score xtrain ytrain, reg.score xtest ytest, and CCP alpha is the x label and accuracy is the y label. And then we are plotting using matplotlib. And then if we shift enter this, we will get the plot. Now the plot is shown here. Yeah. So how do we select the best CCP alpha from this? It will be our new question. So over here, if we try to look, this thing, okay, this is right. So over here, if we try to look, alright, so over here we find that this red line is nothing but testing, and magenta line is nothing but training. So what is happening is, training is coming like this steeply down, and testing is coming something like fluctuating like this in between. Too much of fluctuation over here, and then steeping down, and then steeping down, and then ending here. So this is the kind of situation which is happening over here. So we have to find the CCP alpha in this fluctuation only. Fluctuation in the sense, after what sudden cause or what sudden parameter the testing score just rapidly decreased down. So we observe that over here the crowd is over here, the main crowd is over here. So this entire thing is lying in between what? It's almost lying in between 0.00 to 0.0025, right? So we will be applying our CCP alpha values in list in between these values, that is 0.000 to 0.0025. So we will be applying that kind of logic here. So here, that is what I have written. Possible values can lie from 0.0025. Note that this is 0.025. I am saying 0.0025, which is somewhere around this path, okay, to 0.0075. Now 0.0075 is still less than 0.002 0.025, right? So yeah, this will lie in between this. So if, for example, if I keep my CCP alpha value to be 0.0085, and if I try to run this, you see this, how short and simple this decision tree is, or decision tree regressor object is. Okay, how short and simple the decision tree was made. And you can see MSC also, at each node MSC was constantly decreasing. It went till 0.13, here it went 0.084, and it classified correctly 106 samples. So MSC is falling down, you can see. Instead of going too deep, you are going to till an optimal deep. That is the main name of cost complexity pruning path. Now we will try to do some hyperparameter tuning now. So decision tree model is here and random forest model is here. So if you notice that this is a kind of JSON, which is this is a kind of JSON which we are using, and JSON is nothing but nested dictionaries inside it. Okay, so random forest model, random forest regressor, and an n estimator is this, criterion is this, max depth is this. How on earth can we know this? These parameters are existing. Just click over here and then just shift and tab. Once you shift tab, just expand the widget and then scroll little bit up, scroll this up, and over here you can see this max depth, min sample split, min samples leaf, min fraction weight, max features, min impurity decrease, bootstrap, n jobs, random state, verbose, CCP alpha, max samples. Everything is everything is given here. So based on those criterions, I'm using that, and then I'm executing this. And this is, as this is a randomized search CV, this would be a little bit fast. So for model name and MP in params.items, what will be the param.item here? Params.items will be random forest, decision tree. These are all the no, what are params.items? Params.items are this thing is nothing but params.item. This thing is nothing but params.item. Okay, so params.item is nothing but key with the value. Okay, so for model name MP in param.items, randomized search CV is equals to MP of model. MP of model is what? Random forest regressor. And param distributions is equals to MP of params. MP of params is this. CV is equals to 5, cross validation. N iter, that is number of iterations, and scoring. And you will be applying this algorithm on the randomized search by using the metric known as negative mean squared error. Basically in regression we use negative mean squared error, in classification we use accuracy. Okay, we can use any other metric as well, but most commonly used are these only. So I'll be going with this. And verbose is equals to 2 means it will show us what all kind of this is doing. At the end of each cross validation, we will know the criterion, max depth, max features, min samples, and also the total time which it took for computing the cross validation. And then clf.fit xtrain, and then scores.append, model name, best score, clf.best score. So this CLF, that is nothing but randomized search CV object, it has few parameters named as best score, best estimator, and best params as well. Okay, so I'll be storing this into a list. So this list will basically contain a dictionary, and this dictionary I will convert into data frame so that it is easy for me to know which algorithm I have to select. So I'll execute this. I'll press shift enter, and this will take a little bit time. As we can see, total time elapsed is 0.2 seconds, 0.2 seconds. Now here it is gradually taking more time, because gradually these estimators will also increase, and the CCP alpha values will also increase, and max depth will also increase. Again, I will say here np.linspace. I forgot to say np.linspace. Linspace is nothing but linear space, where starting is 100 and ending is 1200, and 10 is nothing but skip. Okay, so from 100 to 1200, you take any 10 values. You take any randomly chosen 10 values. That is the meaning of np.linspace. Linspace means linear space. So from that particular linear space, you will start from 100 and you will end at 1200. In this particular 100 to 1200 range, randomly pick any 10 values. That is the meaning of it. Okay, So other things are self-explanatory, and then over here it is taking a little bit time. As I said, that as number of estimators increase and max depth increases and CCP alpha increases, these things they increase a little bit more. Okay, so let's just wait for the results, and we'll catch up in the next video.